Hey, honors pre-calc. Today we're going to be learning lesson 3.3, properties of logarithms. So last lesson we learned what a logarithm is, how it's the opposite or inverse of an exponential function. And today we're going to expand our knowledge of logarithms and talk about some properties of logarithms in different types of expressions. The essential question today is, how do properties of logarithms compare to properties of exponents? We are going to use product, quotient, and power properties to write log expressions in equivalent forms. Excuse me. And you should already know what a logarithm is, and you should already know the properties of exponents. That just means kind of some of the different ways that you can manipulate numbers with exponents and still stay equivalent. By the end of the lesson, you'll be able to do something called condensing a logarithmic expression to make this on your screen appear as just one logarithm instead of two. All right, so I'll pause this and we'll head over to the notes. Okay, so here are our notes. Again, 3.3 properties of logarithms. First up, we have something called the change of base formula, which is if log base a of x is our original expression, we can rewrite this as log of x over log of a, with the base being any number, including e, right? ln means log base e. B here just represents that the base can be any number. If we just write log x, we mean log base 10. So the bases can both be 10, the bases can both be e, the bases can both be anything. This was really helpful, this change of base formula, back in the day when I was in high school, and we didn't have TI-84 calculators. Everybody had a TI-83, and the TI-83 didn't have the features of the TI-84. So let me just kind of show you what I mean. We're going to jump down to example 1. We'll come back to the rest of those definitions. But in letter A here, we're going to use the common log or base 10 to evaluate this. Now on the calculator, we already know, and I'll show you in case you forget, that if you press math and then we go to all the way to the bottom to A, that allows us to change the base. So we could have put a 4 here and then a 25. And remember, this is asking the question, 4 to what power equals 25? And the answer is 2.3219. So 4 to that power equals 25. It makes sense because 4 squared would be 16. So it's a little bit greater than that. So it's a little bit greater than an exponent of 2. But another way to solve this would be if we set up an exponent, or sorry, a fraction here. And if we do log of 25 over log of 4. That is the same answer. So that's kind of a shortcut if you don't want to go into the math menu and change the base, or if you have a calculator that doesn't have that first feature, then you can use this, okay? So I usually remember it as the number that visibly appears at the bottom here is the one that goes in the denominator when we type it in. But we have log of 25 over log of 4. That equals approximately 2.3219. All right, very good. All right, we can do the same thing for letter B. So if it's log base 2 of 12, we can write it as log of 12 over log of 2. And if we type that into our calculator, we're going to get 3.5850. Over here for C and D, we're going to use the natural log to rewrite the bases. So instead of writing log of 25 over log of 4, we're going to write the natural log of 25 over the natural log of 4. And if you're tracking here with me, like it says up at the top, these really should be equal. And so I'll show you the first one on the calculator. We can do natural log of 25 over natural log of 4. And you can see we get the same exact answer. And in the last one, it should be the same thing again. And if you type that in, you're going to get 3.5850. All right, let's keep going. Example 2, using properties of logarithms. So if you go back up to the top here, there's really 3 properties of logarithms that we're using, and here's the natural log versions of the same properties. So no matter what the base is, if you have a u times a v inside of a logarithm, we can separate it into 2 different logarithms that are added together. If there's division inside the logarithm, we can separate into 2 logarithms that are subtracted. And if there's a number that has an exponent inside of a logarithm, it actually equals the same thing as if that exponent is in front as a coefficient multiplied by the log. And we're going to be applying that in example 2. So we're going to write each logarithm in terms of natural log of 2 and natural log of 3 here in letter A and letter B. And this is kind of weird, but it is a cool way to kind of first experience this. So the natural log of 6, we know that 6 equals 2 times 3, right? So there's really no reason that we shouldn't be able to write this as this. And now we know from the properties at the top of the page that this equals the natural log of 2 plus the natural log of 3, right? So I am going to box that. That is our answer. We wrote it in terms of natural log of 2 and natural log of 3. The question didn't ask us to actually evaluate it or give a decimal answer. We're just manipulating the expression. In letter B, we have a division question, which means we can rewrite this as the natural log of 2 minus the natural log of 27. But the first term is in terms of natural log of 2. The second one doesn't have either of these things in it. But what I am thinking about is that I know that 27 is the same thing as 3 cubed. So if I use that property, and then I remember that the exponent can be written as a coefficient, we suddenly get exactly what the directions ask for, okay? Let's try letter C. Rewrite and simplify the logarithmic expression. Now this question isn't super, the directions aren't super helpful, right? It's not very specific. So I'm going to guide you through what I'd like you to just see is possible in this question, but don't worry too much about the directions. So the first thing that we're going to do is separate the 5 and the e to the 6. So since these two things are multiplied together inside of a natural log, just like we did in letter A, we're going to rewrite this as the natural log of 5 plus the natural log of e to the 6th. And then we remember that this 6 exponent can be written as a coefficient. And the natural log of e, that really means log base e of e, or e to what power equals e. That just equals 1. Natural log of e is 1. And you can type that into your calculator if you want to check that. But we're going to just get natural log of 5 plus 6 times 1. So this just turns into natural log of 5 plus 6. All right? Down here at the bottom, find the exact value of each expression without using a calculator. So now we're going to try to use these properties to see if we can rewrite these. So for this first one, whenever I see a root inside of a log, I'm going to rewrite it as an exponent instead. And the cube root means 5 to the 1/3 power. Remember, if there's a root, it always means it's in the denominator of the exponent. And this exponent can be rewritten as a coefficient. And now I have that magical log base 5 of 5, which just like when we had natural log of e, that equals 1, right? It means 5 to what power equals 5. So that's 1/3 times 1, which we can just write as 1/3. In letter E, I am going to bring both of these exponents down as coefficients. And now we have natural log of e's, which become 1. So this is really 6 times 1 minus 2 times 1. And that is obviously 6 minus 2. And so we get 4. And in the last one, we always really like it when we can get the base and the number to be the same inside of a logarithm. So I'm going to rewrite this as log base 3 of 3 squared. because 3 squared is 9, but now this number matches this number. I'm going to bring the exponent down as a coefficient. And then this really just equals 2 times 1, or 2. So that's how you use some of the properties of logarithms. Now we're going to talk about expanding and condensing logarithms. The directions are at the top of the first page. So we're going to start with expanding. And sometimes this is really helpful, especially when you get to calculus. You're going to have to do some things called derivatives and integrals of expressions. And when you have a logarithm, it's really helpful if you can expand it so that it's much simpler to kind of take the integral of each term separately instead of all at once. And that might not mean anything to you right now, but that's just kind of a preview of why you're going to need to know this. But anyway, to expand logarithms, there are 2 things we need to know. Exponents must be written as coefficients, and radicals must be written as exponents. We're also going to try to have only 1 term inside of each logarithm. So let's see if we can apply that. So in example 3, part A, log base 4 of 5x cubed y. So I see 3 things, the 5, the x cubed, and the y, that are all multiplied together inside of this logarithm. So I'm going to separate this first into 3 different logarithms, because that's part of expanding, right? We're going to try to make it longer or bigger. And each log itself is going to be simpler. So we're going to have log base 4 of 5 plus log base 4 of x cubed plus log base 4 of y. Every term now has a log base 4. And so our expanding rules said, number 1, exponents must be written as coefficients. Okay, so I do have an exponent here. So I'm going to write it as a coefficient in my next step. And radicals must be written as exponents, but I don't have any radicals, so that means we're done. This is our expanded form of the original expression. Okay, let's try letter B. The first thing I'm going to try to do is separate this, and I'm going to separate because of the division into the natural log of the square root of 3x minus 5 minus the natural log of 7. Now, according to my rules, radicals must be written as exponents. So I'm going to change this square root to 3x minus 5 to the 1/2 power. The other rule said exponents must be written as coefficients. So now that I have a new exponent, I'm going to need to write it as a coefficient in front of the natural log. And we are actually stuck here. So this seems like we still have a lot of stuff inside of this first natural log, but there's nothing we can do to separate this or expand further because there's a minus in here. If there's division or multiplication inside of a logarithm, we can separate. If there's addition or subtraction that's inside, we can't separate it. And that's easy to mix up because multiplication and division turn into addition and subtraction, but we can't start with the addition and subtraction when we're trying to expand. So that is how this is stuck. Letter C, the natural log of x, y, z squared. So first, we're going to separate that into 3 different natural logs. Okay, and then the only exponent we don't have any square roots. We just have this 2 exponent that can be brought down in front. And that's it, we're done. I want to return to the beginning of this question for just a second and make sure that you're aware that this 2 could not be brought in front of the natural log in this step because the exponent here is only on the z. It's not on the x, y, z squared. So maybe we can write this note at the top that the natural log of x, y, z squared does not equal to natural log of x, y, z. But if it was this way, then it would equal this, because if the whole thing is squared, then you can bring the exponent down in front. All right, so that's what we got for that one. Let's look at example 4. Now we're going to be condensing. So we're going to start with the expanded form, and we're going to have to condense it So if we look back at the beginning, we've got some rules here. So first of all, we're going to be trying to, in number 3, we're going to try to have a final solution that only has log or natural log written once. And this time it's kind of the opposite of expanding. The coefficients should be written as exponents instead, and fractions should be written as radicals. So let's try this in letter A back here. So, excuse me, I have a coefficient that should be written as an exponent and another coefficient that should be written as an exponent. So I'm going to do that first. Log x, kind of wrote that x wrong, but we got it. Log x to the 1/2 plus log of x plus 1 cubed. And all fraction exponents are supposed to be written as roots instead, like this. And our final answer should only have one logarithm. So since this is addition inside of 2 logarithms, or in between 2 logarithms, we can combine and multiply the results. So it's going to look like this. And in the final answer, we only wrote log once. All of this inside of the log. And right now, it's kind of hard to tell if the log is just of the root x or the whole thing. So I'm going to put an extra set of brackets so that it's clear that all of this is inside of the log. All right, let's try letter B. We've got a coefficient, so I'm first going to write that as an exponent. And then I have subtraction in between 2 natural logs, so I'm going to write this as the x plus 2 squared is in the numerator, and the x is in the denominator. There we go. Next up, what I personally am going to do first in this one is deal with the inside and then deal with the 1/3 afterwards. You're going to get the same answer no matter which order you do this in, but let's try this. So I'm going to combine these to be 2 things multiplied together with the 1/3 still hanging out outside. X times x plus 1, like that. And then the 1/3 can become an exponent. But make sure it's on the entire inside, not just the x, not just the x plus 1, on the whole thing. And since that's a fraction, I'm going to rewrite this as a root, and it's going to be a cube root. So it's going to be log base 2 of the cube root of x times x plus 1. There we go. And finally, in letter D, this 2 can become an exponent. And then we have subtraction within or in between 2 logarithms. So this is going to become division, log of x over x plus 1 squared. All right, so that is the last question. You all are now pros at properties of logarithms. I hope that made sense. Please let me know if you have any questions, and have fun with the worksheet. And I'll see you real soon. Have a great day.